Welcome to this new lecture of solar photovoltaics course, Principles, Technologies and Materials. So, we have been talking about generation 3 solar PV technologies, and we just initiated our discussion on organic solar cells in the last lecture. So, let us just recap the last lecture. So, in the Gen 3 technologies, we have organic solar cells, we have perovskite solar cells, and we have dye sensitized solar cells. And this perovskite is actually a direct extension of dye sensitized solar cells. It has evolved from the same technology. It's just that it uses different materials. You also have copper zinc tin sulfide CZTS and quantum dot solar cells in the same. So, if time permits, we will discuss at least CZTS in this lecture. So, we were talking about organic solar cells. So, organic solar cells use organic conducting polymers, or rather semiconducting polymers. Polymers are generally insulating in nature, and it was after a pioneering work of Heger, Shirakawa and McDermid, we are now having doped polymers which are semiconducting or conducting in nature, and polymers such as P3HT, PCDTBT, these are all thiophene or carbonyl or benzodiazepine based materials. So, there are various formulas, pretty complex formulas, but let us just have a look at the acronyms PTB7 etc. They have emerged as choice of materials for these solar cells. Now, these plastic based solar cells have certain advantages. They are easy to synthesize, and in principle they can be low cost, and they can also make flexible plastic solar cells which could be useful for certain applications. Another advantage of these is that they have high degree of tunability. So, high degree of tunability because they are synthesized in lab through chemical routes. So, this high degree of tunability allows tuning of properties such as band gap. So, these are certain advantages, and we were also talking about certain disadvantages. These materials are basically, you can say, conjugated or pi conjugated polymers. Okay. Where conduction of electrons happens between between the pi bonds or the pi backbone of the pi segment of the backbone, and this happens by a doping. So, doping causes pi conjugation leading to conduction. So, conduction does not happen in sigma bands, it happens in the pi bands, or pi electrons are the responsible for conduction. So, we cannot go into details of how the conduction happens, it is just that you have to read more about organic semiconductors. There are plenty of literature available on organic semiconductors, but what they have something with regard to solar cells is that they have what we call as binding energy, exciton binding energy. So, binding energy of exciton in these materials is high. This is a drawback in these solar cells. So, this is the drawback. They have high absorption coefficient because they are nearly direct band gap semiconductors. Since they are amorphous in nature or semi crystalline in nature, they tend to have band structure which makes them almost like a direct band gap semiconductor. They have high absorption coefficient, and they also have another problem, that they have low diffusion lengths. So, carrier diffusion length is low carrier diffusion lengths. This is of the order of few tens of nanometer, and this is also a problem. So, on one hand you would like to maximize the thickness because of high absorption coefficient, so that you are able to absorb maximum amount of light. So, on one hand we have a conundrum that because of this we would like to maximize the thickness, but low carrier diffusion length cannot one cannot indiscriminately increase thickness because carrier diffusion length is lower. So these two factors are, you can say, they are contradictory, and this poses a restriction on the thickness of material that one can use. So as a result, there are various designs which have been proposed for making organic solar cells. So we have three designs here. One is designs in organic solar cell. So generally, initially people used to use single junction solar cells. We were talking about that in the last class. So what you have a metal on one side, then you have another polymer, then you have a polymer in the middle, then you have another metal in the on the other side. So this is metal 1, this is metal 2. So for example, this metal 1 has a so this is semiconductor. So you can say this is organic semiconductor, and this is electrode 1 and this is electrode 2. Let us say this electrode has a work function of 3.2 electron volt and this has a work function of 4.8 eV. These two have to have different work functions so that you have enough. So they give rise to electric field which can be used to break the excitons. Okay. So as the light falls on it, the excitons are created, then excitons move towards one electrode. So generally light will not come in this fashion, your device will be in this fashion. So this will be substrate, this will be electrode 1, this would be polymer, and this would be the electrode 2. So light will come in this fashion. So obviously from the top there will be more excitons which are created on the top than in the bottom. As a result, excitons will diffuse towards this electrode. So when exciton diffuse to, this thickness of this polymer is determined by exciton diffusion length, which is very small. So as a result, these devices are not very thick, they are very thin. So since they are very thin, they cannot absorb a lot of light. So which means they cannot, low thickness, which means smaller absorption. So as a result, quantum efficiency of these devices is generally lower because they cannot absorb a lot of photons. So what happens here is when the exciton reach this interface, let's say, these excitons, because of the built-in electric field, they get dissociated. So one carrier will move here and another carrier will go there. So for example, in this case, if you have this as at 4.8 eV, this has 3.8 eV, so this can be used as a cathode and this will be used as anode. So holes will be collected here and electrons will be collected here. Okay. So the main problem with this device is that this has lower, so for example, materials like you can make a device between calcium MEHPPV, which is a polymeric material. So it's a phenylene based material, PPV, MEHPPV, and ITO. So ITO is one electrode, calcium is another electrode. So ITO has a work function which is higher as compared to calcium. Calcium is a more reactive metal. So in these devices one obtains smaller efficiencies, but this is for example one of the devices which have been used in these materials. So efficiencies in these devices will be less than 1 to 2% generally, smaller efficiencies. People have demonstrated higher efficiencies, but getting higher efficiencies is not easy in these devices because of limitations of thickness. So because of this problem in limitations in thickness, then somebody came up with the concept of bilayer solar cell. So bilayer solar cell is pretty much, it's just like a so it's basically you can say it's a heterostructure. just like a PN junction solar cell in 2G devices. So what happens here is you have a, so basic structure is you have a bilayer. So you have a donor, you have acceptor, and then you have electrode 1, and then we have electrode 2. This is the basic structure. In between you can also have sometimes carrier selective layers here and here. So you can have these are carrier selective layers such as hole transporting. So to ensure that, so let me just write in a darker color. So this is, you can say, to ensure that a particular carrier reaches the electrode, right. So basically you can have electron selectivity and hole selectivity. Okay. So these devices generally, so what happens here is you provide a junction in between. This is the junction, this is the interface. So you create excitons, excitons moved. So generally the absorbing material in this case is donor. Okay. Donor is the you can say photoactive layer in most cases. Donors have better absorption for light as compared to acceptors. So your light will fall here, you will create excitons. These excitons will move towards the interface, and because of differences in HOMO and LUMO of the donor and acceptor, we will have an internal electric field which will break these excitons into free charge carriers, which will then move towards the electrode. So what you will have is, you will have, so first is absorption of light, then you have exciton formation, then we have exciton diffusion to the junction, and then we have exciton dissociation, which happens because of differences in the energy levels of donor and acceptor. And then we have, so just like you have differences in the Fermi levels of p and n type, here we have differences in the HOMO and LUMO levels of these two semiconductors, which, so basically HOMO of one and LUMO of another forms the minimum energy gap, and this provides the built-in field. So exciton dissociation. So what will happen is that you will have, so this is the, for example, donor, this is the acceptor. So this gap, so this is LUMO, this is HOMO, this is LUMO, and this is HOMO. This gap provides the built-in electric field to break the exciton. So this is for example donor, and this is acceptor. So once the carriers are broken, they will move towards either side. So as a result, you will put a metal on both sides and they will get collected. So exciton dissociation, then we have carrier transport, and then we have carrier collection. So this is basically a heterojunction concept in which we have a bilayer of donor and acceptor, and these can give you fairly high efficiencies as compared to, so these have given efficiencies of the order of 4 to 5% latest. So for example, you can have a junction between one of the first junctions that were made was, so on a glass substrate we have indium oxide electrode, and then we have what we call as CuPC polymer, and then we have PV as another polymer or organic material, and then we have silver as a electrode. So when you have these devices, then silver acts. So in these cases, what happens is that you have so you can max. So let's say if the device thickness in these cases can be about 50 to 80 nanometer. If your diffusion length is about, let's say 75 nanometer or so. So you can have diffusion length is about 10 to 20 nanometer. Sorry, I am saying 10 to 20 nanometer. And in this case, so for either side of the junction, you can have about 20 nanometer. So you can have about 40 to 50 nanometer thickness. So roughly 40 to 50 nanometer thickness is possible in these devices. So this can vary from 10 to 25 or so, something like that. So this can give you 10 to 25 nanometers of thickness. So you have, so on the donor side, so this is for example, you can have a configuration like this. You can have donor, you can have acceptor, this is the junction. So on the acceptor side, let us say we have cathode, on the donor side we have anode. So you have hole collection on this side and electron collection in this side. So it depends upon the energy levels of donor and of anode and cathode with respect to HOMO and LUMO of the two. So if you look at this configuration here, so you will create electrons. So electrons will go like this, they will get collected here, and holes will go like this, they will get collected here. So this is electrons, this is holes. So here you will have hole collection, and here you will have electron collection. Okay. So basically, where will electron and where will hole go, that will depend upon the matching of energy levels of metals, both metals with respect to the HOMO and LUMO of the semiconductors. So this is a typical bilayer solar cell. That is, one can also make a so for example, a very nice structure is for instance, we have CuPC, then we have C60 fullerene, and then there is a layer of PCP, which is basically a carrier selective layers, and then we have aluminum on this side, and then we have ITO on this side. On this side we have a thin layer of PE dot. So this is PE dot PSS. So these are carrier selective layers, BCP and PE dot, they are carrier selective layers. So this is for hole transport and this is for electron transport. So what will happen is that your energy levels are aligned in such a manner that hole and electron can move in either direction. Okay. So this PE dot will allow only the hole transport. So you have hole collection on ITO and you have electron collection on aluminum. So holes will be blocked by this layer. Okay, they will provide an energy barrier to the holes. In some cases, what you may have is you may have both electron and hole towards either of the electrodes. To prevent that, you use these carrier selective layers which provide a barrier for hole or electron entry to the respective electrode. So if you have anode must collect only holes, not the electron. So otherwise you will have loss of electrons. So as a result, P dot is put in, which is a hole conducting but electron blocking. Similarly, on this side we put a layer of BCP, which is electron transporting but hole blocking. So this is a concept which is used in organic solar cells. So for example, these kind of structures can give you fairly good efficiencies of about, I don't know, about 2% or so. So these are generally lower than 5% efficiency devices, bilayer devices. So to improve this solar cell, what we had was, because the device thickness is still lower in this case, device thickness, the absorption coefficient is, absorption of light is limited. So to overcome this, people came up with the concept of bulk heterojunction. Bulk heterojunction solar cell, the concept is different here. The concept is, if you cannot bring the carrier to the interface, you bring the interface to the carrier. So what it was basically mixing of, based on mixing of N and P type acceptor and donor at nanoscale. So basically what it was, you mix these phases in such a manner. So you have one as, they have to be mixed in such a manner so that there is a continuous contact to the electrode, okay, something like this. So let us say if this is this blue, this is N type material, this would be a P type material. So wherever you create the exciton, it will always find an interface now in this composite form, provided the phases are distributed in such a manner so that N type phase, so that one phase has, so each of the two phases have continuous connection with the electrode. If you have broken paths, then carrier will not be able to reach the electrode. So this, the requirement is, so you basically what you do is that you increase the interfacial area between P and N phases, so that exciton finds an interface, because interface is the one which provides the built-in field for it to break, okay. So exciton finds an interface before recombination, before it recombines and loses itself, okay. So so the idea is to increase the interfacial area. The probability to find the interface within the diffusion length is higher because you have mixed donor and acceptor at the nanoscale. So this concept is a very useful concept, and this gives rise to, so for example, the one schematic could be, you have a electrode, one metal, and then you have another metal on this side, all right. This is, let us say, cathode, and this is, let us say, anode, okay. And in between you have intermixing of phases in such a manner so that you have this phase at, so this is the ideal morphology you would like to have. You have these nano structures of, so let us say this is the donor phase, let us say this is P3HT, poly-3-hexylthiophene, and this is PCBM. So in such a manner your holes can, so since you can create a lot of light, the exciton will always find an interface, you have a lot of interfacial area. The carriers, the holes will transport this way because this is a hole transporting material, it has a better mobility for hole, the donor phase, whereas the acceptor phase, which is the, so these would be a little longer than this, and so the holes will transport this way and your electrons will transport, they will go through here, electrons will transport. So they have this narrow structure in which electron will move towards the cathode and holes will move towards the anode. Electrons will transport in the phases like PCBM, which are acceptor phases, but they are electron conducting. You can say these are electron conducting, they have high mobility for electron, and these are hole conducting phases. Terminology is slightly different as compared to normal p-n junction. The donor phase is P3HT, which is hole conducting, and the acceptor phase is the one which is electron conducting PCBM phase, something like C60, it is a fullerene. So, but the requirement is that the phases must make a continuous network so that there is a complete continuous path for electrons and holes to reach the electrode. If by chance you have so this is a good structure to make. Suppose you have this structure on the other hand, which is like this. So suppose you have a phase which is present in this fashion, then you will create excitons will be broken, but carriers will not be able to reach, because this phase has no contact with the electrode. This is lying isolated manner. So, this will reduce the performance. So, this is not desirable. We need a continuous, we need a continuous network, so that phases are closer to electrodes. That is how you would like to have an interpenetrating network. So, this is called as what we require is interpenetrating network. So, in reality you would like a structure like what it is shown here. You would like an interpenetrating network like this. Okay, this is what you would require in practice, in theoretically, but what we get in practice is a little diffused kind of structure. So, what I will show you is that image of what we get in reality. So, in reality we will get a structure like this. So, this is basically a solar cell which uses the ITO electrode and zinc oxide as electron transport layer, P3HT PCBM as a donor acceptor layer, and then on top we have moly oxide as a hole transporting layer, and then we have silver as a top electrode. So, this is, you can see there are different phases. They are dispersed at nanoscale. You cannot see. So, this is an atomic force microscope image. You can see the whole image size is 500 nanometers. So, the feature size here is of the order of about 20 nanometers or so. So, there is a mixing of phases, two phases at nanoscale with feature size of few tens of nanometer. Okay. So, in reality this is the kind of microstructure that we obtain. So, this is for a P3HT PCBM. P3HT is donor, poly-3-hexyl thiophene, PCBM is a fullerene which is acceptor. So, in reality what we get is a structure like this, and if I give you an example of this solar cell, so you can have things like, you can have a glass substrate. On a glass substrate we will have indium tin oxide electrode. Generally we also have a hole transporting or electron transporting layer, such as a polymer called as P dot or oxide called as nickel oxide, which promotes the hole transport only, so that on ITO electrode only holes are collected. Then in between, so we have this network of phases. So, you can say we have a nano structure. We can say donor acceptor mixture. Okay. Then on top we have a so this is a electron transporting layer. This is only to ensure that only electrons cross through the this layer. So, this could be something like lithium fluoride, and then on top we have electrode which is aluminum. So, in this case aluminum acts as a cathode where electrons are collected, ITO acts as an anode where holes are collected, and the donor acceptor junction is separated by two carrier selective layers. So, here the thickness is of the order of about 100 nanometers or so. This thickness is higher than what you get for bilayer and single layer solar cells. As a result, they are better. and on top we have very thin layers of carrier selective layers which are of the order of 10 to 30 nanometers, and on top and bottom we have 2 electrodes. So, light comes from the glass slide here, and these solar cells, best solar cells nowadays give you more than 10% efficiency that are available. So, we will look at some of these in the next class. Thank you.